Okay, I'm Craig Nelson from NIST in Boulder, Colorado, and I'll be the session chair for digital techniques for time and frequency control. So without ado, we'll start with Claudio Calosso with paper number 7391, The Digital Revolution, also for timescales.
Thank you, Mr. Chairman. So thank you all for being here. I tell you something, what I've done by using low noise digital electronics also for timescale generation. So digital electronics allows you to take advantage of the digital revolution that happened in the mid of the last century when we switched from analog to digital. And the basic is that with digital you can directly deal with the information. With timescales, apparently at the highest level, the information is processed, as you can see in the circular T, where all the measures from the participating laboratories are combined to determine UTC. And in the end, UTC is feedback to the laboratories so they can correct their local implementation. But however, in the end, what is delivered is a real signal, so in the end voltages, that in turn are obtained by combining other voltages, other sinusoids. And at this level, there is something that we can do and improve. So these are the signals that are actually delivered, so a sinusoid from an atomic clock, and then 1 pulse per second obtained by deriving them. And if you want to have a good time scale, you have to minimize the time error between the real implementation and the ideal one. The time error, in turn, can be derived by the phase, by dividing it by 2 pi nu 0. And it has two components, a deterministic one that can be predicted, plus noise. And the same happens also to the PPS. Less than the aliasing. So the goal is to compose clocks, so the voltages at their output, and this is easily done if they were continuous voltages, for example by means of a network of resistors. And you can see here the clear improvement because the noises here are uncorrelated. The same holds also for sinusoid if they are aligned, as you can see here, the noise is less. If they aren't, then you lose your signal, and you need an additional layer of microstepper that realigns all the signal. And this is possible because an algorithm tells them what to do according to the measurement of the phase meter that check if they are aligned or not. And at the same time, the algorithm set the weights. So this is a superset because in reality only one clock propagates and it's called the master clock. Other laboratories have 2 clocks, but the second one is only used as a backup, and in the end the short-term stability is the one of the master clock. So it's better to use a weighted average of the clocks. It's possible to generalize a little bit more the scheme by accepting arbitrary frequency, and this can be done by using a layer of synthesizers. So there are criticalities in these schemes. For example, the switch, the combiner here is very sensitive to the alignment of the sinusoid, but also the microstepper has a residual noise that is not negligible. Here you can see the specification of some commercial microsteppers, but if you measure them, often you see some artifacts of the order of picoseconds that degrades the stability of the clock. Not of a cesium clock, but laser clocks are degraded up to 1,000 of second. And why? What is the key point? The key point is that that scheme is based on the signals, while in the end, as I told you with the yellow highlight, we are interested in the information embedded into the sinusoid. And this is in the digital domain and can be retrieved by using a phase meter and leads to very significant advantages. For example, if you want to steer the sinusoid, here you can see a chirp. Here the chirp is removed. You need an instrument that is bulky, costly, and induces noise, as we have seen. If you work directly on the information, it is sufficient to code a parabola generator that counteracts the parabola inside of the measure. And in the end, after the compensation, you only have the noise. And this fits into a digital component. So the same happens also for the layer of the synthesizers. So here I divided the frequency by 2. And this can be done by using a frequency divider. In the digital domain, you just multiply the set of data by the ratio of the two frequencies, as you can see here. And again, it fits into the same processor as before. There is another interesting point that is represented by the delay in these two representation. So if you use an analog signal, then you have a cable that induces a delay, capital T, plus an additional term. If you have also delay in the digital electronics, this is a gate with the same delay, and in the end, you just read the data after the delay, and you have an error that is proportional to the instantaneous frequency of your data. So in this case, if you want to achieve 1 picosecond alignment, you need more or less 200 micrometer of uncertainty. In this case, if you have a frequency error of 10 to the minus 9 and 1 microsecond of delay, you get 1 femtosecond that is totally ineligible for all the application. So we can rethink the previous scheme by moving the phase meter at the beginning so that we can retrieve the information. And so we have our parabola that are steered by using our parabola generator so that only the noise remain. And in the end, so we don't need anymore the instrument because we already have the data, we just need to transfer them to the algorithm. In the end, we calculated the weighted average, and finally, and only at the end, we put this information into the phase of the output. As you can see here, the advantages are many because there are no additional instruments, so more reliability, less cost, more performance, size, power consumption, aging, and no cabling, so no calibration is needed, and also no aging. And there are the two main applications are that in this way you can generate a composite master clock, and you can use a multi-domain composite clock. So all these instruments now are implemented into a single component, and this is a big advantage. Here is the architecture of the instrument I did to implement this approach. So you can see the layer of tracking DDS, that is the phase meter I implemented for measuring the phase. Then the data enter into an FPGA for integrity check, steering, so the parabola generator, and finally there is the weighted average of the measure. Here it's interesting to note that all the measures are done with respect to the local oscillator that is in common mode. So in the end, here you have the time error between the local oscillator and the weighted average of the steered input. So you can use a servo that forces the local oscillator to track the weighted average of the inputs. And this is the way the phase is put back into the output signal. So this is the instrument. You can see an FPGA in the middle, then a lot of DDS here. There are 16 DDS to implement the phase meter. Then the information is sent to local embedded processor. There is the place for 3 of them. Then there is a switching power regulation with LDO, and predisposition for fiber link. It accepts any frequency from 5 to 400 megahertz in a wide input range, and the output is at 1 gigahertz, that is in the middle between 10 gigahertz, that is the frequency of the comb, and 110 megahertz, that is the classical frequency of the time scale. Low temperature sensitivity, high data rate, and high resolution steering in a wide range, with a very low power consumption. Let me mention the Shannon theorem that says that the capacity of a channel is proportional to the bandwidth and to the signal-to-noise ratio expressed in bit. And this instrument has a low residual noise and high data rate. So it has high capabilities in terms of information processing. So let me tell you a few words about the tracking DDS, that is the phase meter, because the retrieving of the information is a key point. If you are not able to retrieve the information, then you can do anything. It's a tracking DDS, so it's a DDS that tracks the input, and the servo writes a numerical phase, so the DDS is aligned to the phase of the input. And within the bandwidth of the loop, these numbers are representative of the input. The reference is the clock of the DDS, and in the end, there is a residual noise that is the residual noise of the DDS. It has plenty of application, and here we focus in this application. So real-time timescale generation. So the residual noise of the tracking DDS single channel is 1.5 10 to the minus 14 at 1 second in optimal condition. That means at 100 megahertz. If you reduce the frequency and the amplitude, there is a degradation. And there are also glitches and spurs that in turn are not that big. Here is the noise of the tracking DDS in the previous plot, and you can see that the residual noise is suitable also for active hydrogen lasers. And so the ability of the tracking DDS to measure was assessed since 2017, when we used it to measure directly the output at 100 megahertz of the 3 cryogenic oscillators. There we took advantage of the covariance to improve the resolution, the noise at 1 second. But you can do a lot of, it's very powerful for measuring signals, because low noise, it has low noise and a big number of channels. So we use up to now the time processor in this configuration when the information is retrieved and sent to a PC. Now we see what we can do by using the additional functionalities for composing this clock in real time. And for testing it, it is useful to have an emulator. So by using the same board and rearranging it a little, so by going back to the DDS configuration, we can drive the DDS with a noise of generator. We can redesign in a more compact way the test bench. So there is one tracking DDS that is the emulator, and the other one that is the clock composer. So parabola generator to steer the DDS, to drive the DDS, and then the tracking DDS that measure everything. It can be steered, and then there is a weighted average that is used to lock the local oscillator. It has many advantages because you can emulate whatever the clock you want with different noise and different time frequency and drift offsets, but also anomalies. And there is another big advantage is that you can emulate at an accelerated speed, and this is very important for time scale that take forever. And the other advantage is that you know the true time, that is the phase of the local oscillator of the emulator. And this is very, very close to the final hardware implementation of your timescale generation. So first we characterize the noise generator, and we put a very big frequency offset and frequency drift, because this is more demanding in terms of computation in the FPGA. And we put, so here we put 16 different frequency drift, but here you can see only 8 because they are symmetric. The fact that they are symmetric, let me check easily if by averaging them, is there a drift or not. If there is no drift, it's a signature that the calculation was properly done. And another signature is here when you remove the drift, that the Allen variance, Allen deviation follows the 10 to the minus 1/2 law. That was the slope of the noise I put. And here you can see the residual noise, the in-loop noise, so the noise of this point here. That is the ability of the servo to track the average of the inputs. And in this case was not yet tuned, so it was at 10 to the minus 13 at 1 second. Then we started testing the ability to lock the local oscillator to the weighted average of the input. Here two channels were promoted, are not modulated, so that the phase time of the reference is available here at the input of the time processor. And then again symmetrical drifts, but with lower noise, 2 times 10 to the minus 13 at 1 second, and it goes well following the wide frequency noise slope. Here you can see, as before, the in-loop noise, that is the green one, but also the line noise, the line curve, that is representative of the noise at the output of the time processor. And this is because we have here, we can compare the phase, the comparison of the phase of the time processor with respect to the one of the emulator is done by this tracking DDS, that is a phase meter. And having also the absolute time available, we can also calculate the real average of the inputs, and you can, and it is in black. And you can see that you gain as the square root of the number of channels, 14 in this case. So in the short term, it is limited by the ability of the servo to track the average, and then in the long term, the in-loop noise becomes negligible, and the time processor represents the average of the inputs. This is the representation of the signals generated by the emulator, and in line the signal generated by the time processor. And you see the typical behavior of a parabola. And here is when you remove the frequency offset, and here is when you remove the frequency drift. And they are compliant with the numbers I put in the emulator. It's clear here that there is a linear frequency drift, and when you remove the drift, you have a white noise. So this was a test of the steering capability. So at the beginning, so here there are the 4 channels that are used as a reference, and so only 12 channels remains. After the beginning, where the system calibrated, I started to synthesize symmetric frequency offsets, as you can see here. And after a few seconds, I switched on a very, very simple algorithm that compensated for the frequency offset. It was a first-order algorithm, so the compensation was not perfect. But that was not the goal of the test. The test was to check that all the blocks, all the functionalities were running properly. And you can see here that the steered clocks deviates from the white noise slope because of the steering. And since they are steered to the average of the input, in the end they matches the average of the input of the clocks at the input. Okay. This is a test for testing the ability to generate a composite master clock. So currently people use only one clock that is propagated at the output, and this is done by enabling only by locking the servo only to channel 1, for example. And you see that the output has the same short-term stability frequency noise of the input. And here I switched on all the other weights so that now the local oscillator locks to the weighted average of the input, and you see here a clear improvement in the short-term stability of the composite clock. Then, after this test with the emulator, we switched to real signal, and in Besançon there is a very, very nice platform that is called the Oscillator Imp, where you can find all of the kind of sources. So cesium clocks, masers, but also cryogenic sapphire oscillators. And there is a link with Paris to have access to a primary frequency standard through the two-way link, but also a comb and a fiber link. So there is everything. So this is the setup. We connected only some of the sources there. So masers, cesiums, and CSO, and also a microstepper. And this is what is very useful because you connect everything in your lab, and then you can process the information and retrieve a lot of things. For example, the noise of the clocks, but also the noise of the residual noise of the microstepper or of the synthesizer of this CSO. And the trick is that the local oscillator is multiplied by 10 so that the bit note is measured by the tracking DDS. So this is the way the information of the CSO is retrieved. And this is what a recent campaign we did last year, where we characterized this new CSO that here in both. With this scheme, it was possible to compare it with the other CSO, and this is the result, but also with the masers that are better in the medium term, and with the microstepper that provides more, that is a referenced signal. And this is the raw data that we used to characterize completely the new CSO. And if you want more details, there is a poster on that on Wednesday. So here we tested a composite and the multi-domain master clock. And so we removed almost everything, and we kept two masers, two CSO. One is used as a reference, and the other is used as an input. So this is another facility we have because when you do a time scale, it's very difficult to measure it. And having at disposal a cryogenic sapphire oscillator, it was possible to measure the short-term stability and have a representative result. So first we locked the time processor to maser 1, then to maser 2, then to the average of the two maser, and then we switched from the RF domain to the microwave domain by locking the time processor to this CSO. And finally, we estimated the reference noise by locking the time processor to the reference. Okay, so by locking the time processor to maser 1, you can see that the phase noise of the local oscillator is improves at low Fourier frequency, and the locking bandwidth is about 20 kilohertz. Then, and the second maser, maser 2, behaves more or less the same. When we lock the time processor to the average of the two masers, then we see a 3 dB improvement both in the Allen deviation and in the power spectral density. And here the short-term stability is just below 10 to the minus 13 at 1 second. And the average is 6 times to the minus 14 at 1 second. If we switch to the CSO and we lock the time processor to the CSO, there is a big improvement in the short term that now is in the very low 10 to the minus 15 at 1 second, reaching 3.5 10 to the minus 16 as a floor, and this is induced by the CSO themselves. Because the residual noise of the time processor only the contribution of the time processor, is 10 to the minus 16 at 1 second and reaches 10 to the minus 18 at 1000 seconds. And this is a check of the ability to lock the local oscillator at this level. That is a level already suitable for optical clocks. And this is, as a reference, the noise of commercial microsteppers. So, in conclusion, I show why digital revolution is so advantageous for a physical realization of a time scale, and I show you that there is an instrument that is called a time processor that is able to characterize in one shot an entire time laboratory. It is also able to emulate a set of clocks and to compose clocks in real time. So by processing directly the information instead of analog signals, we can easily generate, for example, a composite master clock and a multi-domain composite clock. And let me thank FEMTO-ST, all of these people that helped me during this work. And let me remind Marcus Icardi. Thank you a lot.
Well, thank you for a very nice talk. And it looks like we have about 4 minutes for questions. So could you please use the microphone?
What was your truth standard for all your Allen deviation plots? Was it your time scale itself?
Sorry.
You had all these Allen deviation plots. What was the truth standard? What was the reference that you were comparing them all to?
The truth standard? No.
La verite. You have an Allen deviation. It's between
Yes.
two clocks.
Yes.
So what was the reference clock for all of those plots? The perfect clock.
So here, the perfect clock in the short term was this cryogenic oscillator, because its short-term stability is much better than the one of the masers. So when you lock the local oscillator to the masers, you can check the short term by comparing it with the reference.
Well, that makes sense for the low tau part of the plot. But then you went to where the masers were better. So did you switch as you went along your Allen deviation plots?
This was tested by using the emulator, because with the emulator you know the real time. This is the reference time. So if you want to check the behavior in the long term, you can use this scheme. And in addition, the behavior of electronics in the long term is good, much better than the one of oscillators, because it's phase noise and not frequency noise.
Any additional questions?
Thank you. I think we discussed that previously, but I'm still confused. When you are making a composite clock, don't you think that the one thing that I see would be extremely useful is to be able to have a weight that is different for all the different clocks depending on the different time domain? Can you see an easy way to implement that?
Yes,
algorithmically?
Just change the numbers here. These are
But you need to have a number that is different for 1 second and for 1000 seconds, for example.
You can put a number here. I provided 60 dB, six order of 60 bits for this number. So it's a floating point number with 16 bits for the mantissa and the ability to change the X.
But I think what you need is not a simple number, it's a transfer function. That
yes, if you want, you can put a transfer function, but the important thing is to compose. So you have many layers. This is in the FPGA layer and deals with the short term. If you want to do something more complex, then this is the task of the algorithm. So you first generate a composite clock of all the clocks in the same class, And then the average of the weighted average of the clock in that class is steered by the algorithm, and so you can implement, you can take advantage of the best of each clock in the different region of the deviation.
So we have, I don't know, we're almost out of time. We could possibly have a very short question, maybe. All right, I think we can start moving to the next talk.
Thank you.